this phone to record with the iPhone is so much easier. Okay, so let's look at the first chapter on bonding that you're going to be tested on. How am I doing? Is this on? Am I all right? Okay. So let's look at ionic bonding very quickly, and let's simply talk about it. Wrong book. I need a book. Where's the book? Is there a book there behind you? All right. It has been an uneventful morning so far. Is everybody on the website? Is there anybody still looking? Everybody did it? Ginny, how you doing back there? Did Alex explain everything? You did or didn't? Okay, very good. Thank you, Alex. Well done. Okay, so let's look at the chapter so far. We know what valence electrons are. It seems that we've been already doing this. Don't you agree? Doesn't it seem like we've been doing chapter 7 on ionic bonding for the last 2 or 3 months? Yes or no? Doesn't it feel that way? Jose? Yeah. We talk about valence electrons, the rule that I won't let you say, where every atom must have an octet. I said the word. Every atom must have a noble gas configuration when they bond. That the ground state sounds very stable. If I say to you, what's the ground state of sodium? What's the number of electrons and protons? You say what? What do you say? Look at sodium, Na, first column, 3s1. What do you say? What's the ground state of sodium? What's the number of protons and electrons? 11 protons, 11 electrons. But doesn't that sound nice and stable? It does, doesn't it? It's kind of nice, huh? You know, you like that? Everything's equal, but that's not stable. You put sodium in your hand, you burn a hole straight through your hand. So what does sodium do? It keeps the number of protons because it wants to say sodium, right? Correct? But then what does it do? It gives up one electron to be like neon, right? Why don't I like to call it the Voldemort Rule? I don't use that word, by the way. I just say Voldemort. Why don't I like to use that word? Because it's a little silly. You just simply say that it's like the nearest noble gas. That rule, it almost sounds like you need something to help you memorize that. That you want to avoid the concept and just come up with some kind of brain-dead rule that helps you memorize that. Because where doesn't it work? Where doesn't that rule work? With a very important element, helium, doesn't work. Why would that be an exception? There's no exception there, because that's just what it is. It's when the outer shell is full. It's not a question. It's not a question of 8. It's a question of we're doing what the noble gas does. Clear? Yes or no? Okay. So, what's a cation? Cation is what? Cation is a positively charged ion. Thank you, Arminda. That's nice. Nice recovery. And an anion is a negatively charged. Metals are generally cations or anions? They're what? Cations. You have to know. You have to go back and look over your what? What do you have to go look over? Electron configurations. Anybody have a question about electron configurations? You have to know what's the electron configuration of the iodide ion? What's the short form electron configuration of iodide? What is it? It's going to be what? Iodide. Short form is going to be, what's going to be the nearest noble gas? Garrett? Sorry, I woke you up. My apologies. It is Monday morning or Sunday morning, depending on your point of view. What is it? Krypton. 5s2. 5s2 what? 4d10. And then what? 5p6. Why did he say 5p6? Why did somebody said 5p6. Why did you say that? Is it on? Can I read that? Good. Why did you say that? Why did you say 5p6? Why did you say 5p5? That's iodine. Why did you say 5p6? Is he right or is he wrong? Go ahead. Are you right or wrong? Defend it. You're looking at me like you're not sure. I'll give you a hint. You're absolutely, positively, 100% correct. Because what did I ask for? I asked for the iodide electron configuration. That means it's taking on an electron to be like the nearest noble gas, correct? Yes? This doesn't give you a hint that there's 8 there, does it? Doesn't say 8, does it? So the octet rule would be worthless. But you're getting an extra electron because it's one away from that, correct? It's one away from that. Then you're writing it out and you're putting on, because you know that's 3p5, you put on 3p6. Now you can say, oh, okay, that's right. It's S and P electrons. It's S and P electrons. Those are the valence electrons that you use, S and Ps. Clear? Now, there are certain elements on the periodic table. If you look at the periodic table, okay, at home, get out a periodic table. Transition elements, what general columns of transition elements have the multiple oxidation states? It doesn't really say in the book that all transitions elements have multiple oxidation states. Do you remember what it said in your reading? I think we might be in chapter 8 right now because I do 7 and 8 together. What does it say? What element, what are some exceptions to that rule? There's one column that's a big exception. Actually, 2 elements that are a big exception. You have silver is always plus what? What's silver? Always. I'm sorry you have to memorize this, but you're not really memorizing this because you're doing so much work, you just get used to it. What's silver always? Silver is always plus 1. The silver ion is always plus 1. I think I might even actually be in a little bit in chapter 9 right now. It's plus 1. What's zinc always? Plus 2. Gold. Gold might be in there too, but mainly zinc and cadmium. Cadmium as well. Cadmium is what? Did I say cadmium? No, I didn't say cadmium. Cadmium is plus 2. Zinc, silver. What about iron? What are the 2 major oxidation states? You know what an oxidation state is? What are they called in the book? What is it? No. What's a coordination number? You know what a coordination number is? Look that up. Let's talk about a coordination number. While you're looking that up, let's look up what's a formula unit? What's a formula unit? A formula unit. A formula unit. What's a formula unit? What's a formula unit? Are you reading something from the book, which is fine, but that's not the way you usually speak, so it sounds odd. I don't even speak that way. It's the smallest particle. It's called a formula unit. Yes? Yes, the smallest particle. So that would be ionic compounds. The smallest unit is the formula unit. What's the smallest unit in a covalent compound? Is that on? It's hard to say. Let's move it over this way a little bit. What's the smallest unit in a covalent compound? You know this, by the way. I'm just want to let you know that. Alex, any idea? Starts with an M. You studied them last year. You studied macro something. Mole? No. What did you study? Macromolecules. Very good. What's a macromolecule? Give me an example. Like protein, giant protein, globular protein, macromolecules, yeah. I put molecular. Okay. What is a coordination number? What's the coordination number? This is a little bit tricky. You're going to have to actually memorize coordination numbers, so I'm giving you a hint to put that on your outline, coordination numbers. Tell me what a coordination number is. Anybody look it up? Did you look it up? Shall I read it right from the book? And you see my bald head, I look like a Florida manatee, don't I? Does that look good? Look like a Florida manatee in my top of my head. Mohammed, you're laughing. It's good. I'm glad I can entertain you. I am actually a little entertaining, aren't I? I mean, a little bit, don't you think? I am a little bit, okay. Are you saying yes, give me a good grade, or are you saying yes, you really think that? You're saying yes, okay, so it's a little bit of both. Excellent, okay. I like that, honestly, okay. So coordination number is an ion. The coordination number of an ion is the number of ions of opposite charge that surround the ion in a crystal. So look at the figure below, 7.9. It says, and I'm reading from the book, it says, sodium chloride and cesium chloride form cubic crystals. This is right in your lecture, by the way, on the internet. Make sure you pay special note of that. In sodium chloride, each ion has a coordination number of 6. You see why that is? See if you can pick out a sodium ion. Pick out a sodium ion. Pick out a green one. That's easier. Pick out a green one. How many sodium ions are surrounding it? Now remember, you have a cube on the other side, so you may not be able to find it in a cube. Look at the sodium. You know what? Look at the sodium in the middle of the cube. How many are surrounding that?
4.
How many?
4.
No. You're not looking below it. Above and below, right? So let's see if I can draw this.
5.
No, not 5.
6.
6. Do you see the 6th one? You see that? I'm going to try to draw this. All right? It's going to be in the middle. I don't know how to draw it in the middle, right? It's going to be in the middle, right? You get it? So you're going to have one. I suppose we should draw these lines in, right? Okay, so you're going to have one from here. You're going to have one, let's see. Yeah, you're going to have one like this. You're going to have one like this. You're going to have one like this. Right? Right? It's hard to see. So you have, I'm not doing a good job. So look, I should put it on the board. You see, look at what's in the center of the cube on the left? What's in the center of a cube? A sodium or a chloride? A sodium, right? Now look directly above it. What do you see? Chloride or sodium? Chloride. Look directly below it. What do you see? A chloride. Look to the left and the right. What do you see? Left and right. As you're facing it, left and right. What do you see? All right, what do you see? Chlorides. That's 4, right? Look in front and back. Chloride. So you have it above and below. You have a chloride, right? Left and right, you have a chloride. And front and back, you have a chloride, right? How many is that? So what's the coordination number for sodium chloride crystal? 6. You see how to get it? Now, without looking at the picture, what is going to be the coordination number of cesium chloride? Cesium's in the middle, and what do you have? So it should be 8, right? You see that? So the coordination number of cesium is 8. You have to know this. Clear? So you have to be able to look at a crystal and tell what the coordination number is. Clear? Yes or no? And you have to remember what sodium chloride and cesium are. All right, what else? What about metals? What about metals? Let's look at metals for a minute. What's in kind of like a sea? They call it a sea. You have metals and you have this sea of something in the metals. You have this swarming sea of something. Is it water in the metal or what? What is it? Is what? But I can't hear you.
Is it
Carbon?
carbon?
No. Carbon's a non-metal. What I'm looking at is transition metals, like aluminum, iron. Yeah. What's there a sea of? I think that's what they mention in the book. Don't they say if there's a sea of something? What is that? A sea of something. What do they call it? You guys have been reading, right? I mean, do you realize you have a test next week? What is it? A sea of what, Ginny? Yeah, the valence electrons are just a swarming sea. Matter of fact, they're so loosely held that if I pick up a charge, if I send a charge through this, the electrons are going to go wild. They'll conduct those electrons can be conducted because there's such a tremendous amount of electrons in here, and they just swarm, and they can be conducted right through the metal. That's why they can conduct electricity. Can a ionic solid conduct electricity? May I speak freely? The fact that you guys don't read ahead is very troubling. Plus the fact that you guys are quiet anyway, but this is like torture. Okay, I mean that with great affection. But what is the story for an ionic solid conducting electricity? Kennedy? Remember, I'm in the midst of writing your letter, so I would suggest answering correctly. Yes, that's a threat. I just want you to say hello, Mother and Father Kennedy. That was a threat, yes. Do you know what electricity is? Are you from Earth? So you know what electricity is, right? Do you know what wires are, right? Okay, good. Wires conduct electricity. Would you say that that's true? Metals conduct electricity, yes or no? Okay, good. Now, let's hook up a giant sodium chloride crystal. Can that conduct electricity? I'm not quite sure what that was. Was that so subtle of a no because you were a little unsure? Was that inversely proportionate to your understanding, or was that proportional to your understanding? In other words, you went like this. Does that mean that you're really sure, which I doubt, or you're really unsure? Was there a direct relationship between the passion and drama of that no, or what was it? So will that giant sodium chloride crystal, will that conduct electricity, yes or no? And why?
No.
No. Will someone please look it up? Can ionic crystals conduct electricity? Do it. Do it now, guys.
Yes.
Yes, they can. Is that what it says? You just answered the question way beyond what I asked for, and that's good. That's very good. But I'm asking you a giant sodium chloride crystal. Can you picture it? It's a giant translucent block of sodium chloride that stretches across the room. I'm going to hook my iPod up to it. Is it going to conduct electricity? I'm going to hook my iPod to one side, and the other side I'm going to put in the wall. Will it conduct juice to my iPod? Yes or no? Solid sodium chloride crystal. Mohammed, you answered the question. Do you know you answered the question?
Yes.
So what's the story?
It would not conduct electric current.
That's correct. I feel like I'm pulling teeth. It would not conduct electricity. That's right. Because when does an ionic solid conduct electricity? When it's what?
Melted or dissolved.
Melted or dissolved. You get that?
Yeah.
Okay, good. What's next? You see the metallic bonds and metallic properties on the first page? Know that. That's a hint. Look at chromium, gold, and zinc. Now, let me ask you this. Do metals, transition metals, do they form crystals? I'm asking you, do they form crystals? Baslin, are you on the same chapter that I'm in? You have on your desk War and Peace, I think. Is that the correct book that you're supposed to have? Look at page 210. I'm kidding. No, I'm not about 210, about War and Peace. Look at 210 to 11. Do metallic substances, do metals form, do transition metals form crystals? Yeah, of course they do. Of course they do. Of course they do. Yes or no? Yeah. And what are alloys? Give me a way of explaining what an alloy is. An alloy is like this. You've heard of salt and water, right? And you mix that up, right? You mix that up, right? And you get the salt completely distributed through the water, so you have one phase. What does phase mean? A phase means this is a definition that you've never been aware of. Maybe in middle school they never taught you, but a phase, we're going to be using this word a lot. You ready? A phase is a single set of physical boundaries. This is one set of physical boundaries. Do you see that? It's one set, it's one thing. I go like this, now I have two sets of physical boundaries, right? Or I could say this book has one set of physical boundaries, right? Yes? Okay. I could say this pen has one set of physical boundaries. This calculator has one set of, that's a phase, right? Now it's two phases, right? So if I put salt in water and the salt sits on the bottom of the water, within the beaker, what do I have? I have two phases, right? I stir that salt up and the salt disappears, right? Yes or no? Okay. But what? I have one phase, right? You get it? You sure? Looking at the beaker as well, I have two phases. I have the beaker and I have the water. But within the beaker, I have one phase, right? That's called a solution. An alloy is when you do it with a solid. Two solids go together, completely mixed up, where you only have one phase. Chromium steel. No, gold is an element. Gold is not an alloy. When you take two and you put them together, now, it's not just a random combination of atoms in there. Not random. The elements have a little bit of a crystalline structure. And when you put elements in and they go somehow into that crystalline structure, they will do good things to the structure. How many people are wearing gold right now? Raise your hand. Some kind of gold. Nobody's wearing gold? Gold cross? No, no gold crosses? No? Very amazing. Excellent. Well, gold that you wear is probably 14 karat or 18 karat at the most. What's pure gold? 24 karat. Okay? Yes? That's an gold is really an alloy that you're using. What's white gold? It's not platinum. What's white gold? I was just talking to a jeweler about this. Look up white gold right now. Tell me what it is. Somebody look up white gold. All right, let's do a quick internet search. I want to go white gold, right? Yes? And so first row, white gold. Okay, you got it? First row. Second row, I wanted this half. Okay? Jose to Basil. Okay? Jose, right? Okay, Jose to Basil. I want you to look up different kinds of steel and the percentages of the alloys right now. Steel, chromium steel, whatever. Okay? Cast iron, whatever. Clear? Second half, I want you to look up brass. What is brass? What is the difference between brass and bronze? Okay? Back row, I want you to look up molybdenum steel. Just the whole row, look up molybdenum steel and what's it used for. Okay? And that's it. All right, and we're going to continue to talk about chapter 7 and 8. I'm going to go to chapter 8 now. Chapter 8 we've been working on a great deal. Actually, we've been spending most of our time on chapter 8. So let's go through chapter 8 quickly. Right? Now, if I say to you this. If I say to you, that, let's do that quickly. Right? That would be the ball and stick model, correct? And then it would be 7, 7, 7, right? Which is 21, 22, 26, right? Yes? 26 minus 2, 4, 6, 8, 18. That's already complete, that valence. So that's going to be minus 18, 0. Okay? What's the shape of that? 4 bonds, no extra electrons. It's going to be what? Tetrahedral, correct? Let's draw in our dipoles. Chlorine is 3, right? Carbon is 2.5. Yes? 2.4, 2.5. Remember, if the electronegativity is the same, it's never the same if the elements are different. So just put the arrows somewhere, but make sure they're all consistent. Yes? If it's the same, just put arrows in, because they're never exactly the same. Polar or nonpolar? Are the bonds polar or nonpolar? Are the bonds polar or nonpolar? Bonds are what? Bonds are polar, right? Bonds are polar. 4 polar bonds, guys, right? Yes? The molecule. Polar or nonpolar? The molecule. Nonpolar? These two cancel. Eamon, do those cancel? No, they don't cancel. So it's polar. Right? You get that? Eamon, I'm a little worried. We just did this long lab. You have evidence of the lab on your desk. I'm not quite sure what it is you drew there, but you're getting there. Looks like a square planar without the excess unbonded pairs of electrons. It's not bad, okay? It's kind of scary that I can tell from even here. Isn't that scary? A little scary, yeah. Okay. Now, so that's what we're doing. So that takes care of like the first, gosh, the first three, right? Like the whole chapter, basically. And then there's a few things we've got to look at. Other than that, okay. I will put a message on the bonding page. I'll write a little message on what set of, you know what, I'll put a special playlist up where I want you to look at the bonding playlists, yes? And all the bonding, everything is organized on haiku, right? Yes? And I'll put on a special bonding playlist, okay? And, but there's also, I'll put a special playlist for bonding. That's what I'll call it, special playlist for bonding. And it's like from chapter 15, I think. But it's important because really, you see where it says attract